All right, so I'm going to do the completion on uh, my lecture from this morning, and I'll back up a little bit here. So I'm going to start where I was talking about node recovery. Okay, so what we're doing is we're walking through the log to make sure that we can actually recover our state, because after all, that's kind of the point of us having a log. So the coordinator is going to use a timeout mechanism, and that allows the coordinator to say, I'm willing to wait this long for you to acknowledge the prepare phase. And if you don't acknowledge the prepare phase within that time window, then I'm going to declare you to be dead. Now, normally what will happen, and this is just a general design point, we see this in the project 3, you normally make that timeout period some multiple of the retry count. And the reason for that is because, of course, we have this unreliable network. But at some stage, we have to say, this network is so unreliable, I just simply have to assume that since I haven't heard from you for the last 2.5 years, you're dead. And it's a slight exaggeration, but there's some number. It doesn't make any difference what number you choose. There's always the vague possibility that the acknowledgement is going to come up after that. And that's actually okay. That will work in our protocol as long as we make a decision in the coordinator that the node can then confirm afterwards, life is good. Okay. And why this works is because the node, when asked to prepare, doesn't know what the outcome of the transaction is, because it might say, yes, I'm willing to prepare. I'm willing to roll forward, to commit. But somebody else says I'm not. So as long as the node doesn't have an answer back from the coordinator saying everybody's rolled this forward, then the ambiguity of whether or not we got the node's acknowledgement is still allowable. It's no different than if the node said yes and somebody else said no, or this node said no and so everybody else said yes. It's the same outcome. So in the case where we don't get the answer from the node, it's like, that is still an acceptable uh, path through the system. So it leaves us in a consistent state. When a node does this recovery, it it needs to go through its log. Now, this node has information in its log that says, here's what I actually did. I don't know what the rest of the world did, but here's what I did. And I can reason about what the rest of the world did based upon what I did. I look at my log. I have a log record. So I started a transaction, but I never wrote a prepare or a commit record to that transaction. So I know, since I didn't write a prepare record, I didn't tell the coordinator that I was prepared to roll this transaction forward. So therefore, I know that I can abort this. I can safely abort this. If the coordinator comes back next Tuesday and says, okay, everybody's ready to roll that transaction forward, I can say, no, I'm not. And that will work. That meets satisfies the general guidelines of the transaction. As you can see, those timeouts, we have to be very careful in managing them to make sure that we don't introduce some sort of subtle window where the node gets to reject it. Notice that the node basically has to hang out pretty much forever. Again, going back to the point I made earlier, if this doesn't work, if this doesn't actually happen, then what I have to do is I'll have to intercede manually. I'll have to fix this. It's something I cannot fix automatically. Remember, our systems do not have to fix everything. What they have to do is make sure that when we do something automatically, that we can demonstrate why it actually leaves us in a consistent state. If we have something that happens that leaves us in an inconsistent state, that's outside of our failure model. And that's fine. The right thing to do then is to stop, is to say, we're going to fail stop here, and someone has to come in and fix this. And that works okay. So that's enough for us. So that was what happens when I looked through the log, and this first line here, when I looked through the log and there's no commit. But if there is a commit written into the log, but I don't have the actual decision written in, so I don't know if it was committed or aborted, then the only thing I can do as a node is to ask the coordinator what happened. But what happens if the coordinator's not available? Well, this is kind of one of those interesting issues we're going to have to worry about. We see this in Project 3, where we created this view server that, in essence, acts as a form of coordinator for us. We get the view from the coordinator, and it tells us what the state of the world is. But if the view server is not available, then we can't really do much because we don't know what the current configuration is. So if the coordinator is not available in this model, we can't really do much either. And this is a weakness, and we will have to address that. And that's going to motivate what we're going to be doing over the next several lectures when we start talking about multinodal consensus algorithms. Okay, so just to walk through this two-phase commit as seen from the perspective of the log. So we have our node here on the left that gets, it says, I want to commit this transaction because it would presumably be the one that started the transaction. Calls the coordinator sends messages to everybody that says, okay, let's prepare to commit this. Everybody says, we're prepared. Now we get to make a decision here. But if we look at these logs, what you see is that we don't actually have a record in there indicating that these were in fact committed yet. So the workers, the nodes here, don't actually know what the outcome was. And the only way for them to find out is to actually have another mechanism for calling the coordinator and say, yo, what was the outcome of this transaction? And this is about coordinator failure. So a timeout of a node, let's see, the node sending a commit request. If the commit request itself times out, the node can fail because it hasn't agreed to a prepare yet. So the node can always abort at that point. The node is allowed to reject the transaction, which is kind of weird, right? Okay, I initiated the commit request, but then you call me back and I can say, sorry, I changed my mind. And that would be what I would do if I sent it to you and whatever my timeout period on it has expired. I can now say, you know, I waited around for you for a while and you didn't show up, so I'm done. I'm out of here. And then we write an abort into the local transaction log. Now, if I get to a point where I want to clean my log up and I've got this transaction that I can see the whole thing's there, it was aborted, so I've recovered successfully from that, and I excise it from my log, what happens then later is if the coordinator calls and says, okay, but I want you to prepare this transaction, I can sit there and go, no. And that will lead me to the correct state. This is one of the things that process of walking through and saying what's going to happen if I do this, then what will I do for the next stage, is part of how we start to think about, does our algorithm work? Does it provide us with consistency? As we make these algorithms more complicated, it's going to get harder to reason about. And this is a really important part. And it's going to motivate some of the conversations that we have later in the course about doing things like formal verification. So you can define what your protocol is and you can get a formal verified version of that. And that's its own interesting little exercise. If the node sends a response to the prepare request, probably should say, that's a little confusing on the slide. Node sends prepared response. Well, the node, it sends a response to the prepare message. Then if it times out, then we have to wait. The node can't declare the transaction dead. Only the coordinator can declare the transaction dead at that point. So the node has to be prepared to keep that indefinitely. And this is one of those interesting cases where being able to compact your log becomes an important issue. So let's see. Okay, so transactions outcome is indeterminate. You have to ask the coordinator, but if the coordinator is permanently lost, then you are in a situation that we are not going to be able to automatically recover. It's okay. That's not a failure of the protocol. That is just simply an acknowledgement that there will be failure cases we're not willing to handle. And this is effectively, sorry, the coordinator was on Earth. Earth got blown away by the Vogons, and we're done. Somebody else with more privilege in our system, more authority in our system will have to come and fix this manually. and that is perfectly acceptable. So as I noted, this means that if we really only have a single coordinator with no replication and no backup on it, then it becomes a single point of failure. So we could, in fact, build. So when a coordinator doesn't have high traffic, we could use something like Project 3, where we have the primary backup version. We could do something like that. We could build a primary backup version. We could build a simple quorum replication system. And I've seen that done. And often that's all you need to maintain the consistency of like an infrequently changing database, where you just have replicas and you have a coordination mechanism between the replicas that uses a voting protocol. This is not the voting protocol that I would use there. You could, in theory, use it, but it is possibly one way of doing it. To some extent, the protocols that we see as we move forward and we look at these no single point of failure data replication protocols, what will end up happening is we will have a coordinator, but the coordinator will itself be replaceable. So we don't be in this situation where a single failure is going to cause us a problem. Another interesting approach to the log situation is to keep a replicated log. So that would be one way for us to harden our coordinator. So we could replicate the coordinator log. There are two simple approaches there. One is using quorum replication. That was the Daniel Spector-Thompson paper that I mentioned before. I actually worked for Alfred Spector many years ago, and he went on to work at he ran advanced research at Google for a while, for many years, and then he went on to a company called 2 Sigma, which does high-end financial stuff. And Dean Thompson, who was one of the co-founders of Transarc, company I worked at, along with Spector and a couple of other people, I knew him from that. And let's see, he's worked at a couple of other places since, and I think he was at LinkedIn for a while. I don't know what he's up to these days, but at any rate, it's a very nice, simple, early quorum replication system. And one of the reasons I picked that paper is because it's actually simple enough you can sit down and you can read it without it being super dense and chewy, whereas some of the other papers I gave you are much more recent and they are more complicated. So in this particular case, what we had was multiple log servers, and essentially what they used was a distributed replication protocol that isn't even as strong as chain replication. So we can recover it, and it appears as if it's a single client to the rest of the system, but it has a model where things won't necessarily be present on all of the replicas, but they'll be present on at least more than one replica. So we'll have a quorum of the replicas that will have a copy of this log state. Another approach to this, very different, is like Corfu, which I'll be talking about in a moment, where we have this global shared log, and it provides replication. It gives very good parallelism because you can actually access it in different parts of the log because the log itself is not centrally located. And it utilizes a mechanism of garbage collection that we see in SSDs now, which is to create sparse areas, sparse regions in what they call trim. And a trim is basically a hint that says, I'm done with this. I don't need this, whatever's here anymore. So you can recycle this block of storage. In this case, this block in the log. So Corfu, which is also a Greek island, is a multi-machine distributed log that presents the abstraction of a single log that only allows appending. Limiting it to append makes reasoning about things a lot simpler because that's how we get sharing. I can't actually go and say, I want to write to this place in the log. You say, I want to write to the end of the log, and it allows you to do that. And if you read the paper, they even relax some of that. They have a reservation scheme. So it's an append-only reservation, but then you get to write in the area that you reserved with some interesting behaviors about what we do if you don't write to it fast enough. So that one's a very interesting project. It's a lot more complicated. so you can see on the other end of the spectrum how complex logs can become. It does support compaction using this sparse allocation or deallocation strategy of trims. It does write once semantics. So we have this pre-allocation scheme, but you can only write to it once. So it becomes it is an atomic write. You can only write in a pre-allocated region once. You cannot write on it again. It will actually return a distinguished failure. And you can even use block level replication with it is chain replication. So you can have multiple copies of individual log blocks scattered around underlying devices. And I think I mentioned earlier that one of the tricks this plays is it uses an extra indirection. It uses a table that maps from the virtual log, which is quote unquote infinitely long. It can be up to 8 exabytes long, and that's pretty long. That's going to take us a while to exhaust. And it's only limited 8 exabytes because we have a 64-bit pointer in it, and that limits how big we could go. If that's not big enough, we can certainly increase that to something that goes from absurdly large to incredibly, totally 100% way over the top absurdly large. Doesn't matter. So it doesn't break the model here. So it is considered to be an infinitely growing log. It maps virtual to physical locations. It deletes the storage that's no longer needed when it can. And that means that it can recycle the actual physical storage underneath, even though it never reuses the virtual storage on the top. And if you want more detail, I recommend you go read the paper. The link is in the recommended readings. The next thing that I thought was interesting was this EngraveChain, which is an interesting example of a very specialized log. And this gives you an idea. I'm talking about logging, distributed logging, but now we have logs that are custom built with specific semantics. And one of the reasons I decided I wanted to put this in here is because Corfu said you can only write once, and that gives us some level of permanence. But maybe we actually want to write once and not allow you to delete it. And that happens when we want to have audit logs, when we have strong requirements for maintaining auditing information that can be used to ensure accountability. And where we see this are in places where money or very sensitive, usually because it's worth money to somebody, information are stored. Payment card industry, you'll normally see this by its initials, PCI. The payment card industry standards define how credit card data and credit card information are actually controlled and managed, and they're very stringent. When people build distributed applications, they can be very concerned about PCI and how they isolate the credit card information so the rest of the system is not actually exposed to it. It's pretty interesting. I've seen systems where they don't actually take the credit card information outside of a very small protected core. And that protected core would be using this kind of a tamper-proof log. So I'd actually have a real logging system. GDPR protected data is another example of that. What you want is you want to be able to have some accountability there. So if somebody compromises the data, you want to be able to go back, look, and figure out what actually happened. Where did the data go? What's going on? And healthcare data. Here in BC, it's PIPA that protects us. In the United States, they have a national standard. We don't have a national standard here in Canada. We have provincial standards because healthcare belongs to the provinces. In the US, they have this thing called the Health Insurance Portability and Protection Act, HIPAA, and that relates to protecting people's personal health data. Same basic ideas. Many of the principles are the same. Accountability is a really big issue here. So this has strong requirements. It needs to be distributed. It needs to be Byzantine fault tolerant, because if people can screw with your log, then they can rewrite history. And so we want to prevent that. So EngraveChain is a distributed chained log, a blockchain, and it uses a well-known protocol, the Practical Byzantine Fault Tolerance Protocol. And I've got a link there. You can go look at that more if you want more information. The last one, okay, so right, a little more about EngraveChain. Sorry. So EngraveChain actually does this using an interesting model of where they split the encryption keys. So the place where they actually record the data is encrypted under the key of the entity that records it. And so what gets recorded in the blockchain itself is not the decrypted data, but rather a copy of the encrypted data. Or if the data is too large, they actually say, well, you can just store the hash of the the data in the blockchain. I kind of like the hash actually better, because if you stored the hash of the decrypted data, then you'd have a way or a mechanism for validating that data was properly decrypted after the fact. If you stored a hash of the encrypted data, then you wouldn't actually know if somebody were to tinker with it or tamper with it, because they wouldn't know what you had done. They wouldn't know the key, so you could try to find a different key, and that would create a different set of potential security attacks that I don't even want to think about right now. But at any rate, this is their model. It was a very interesting model where they have these the different entities that are recording information and storing it in this log to encrypt it with their own keys. So that allows different generators to make this semi-visible without compromising their own security. So they're trying to hit this very interesting kind of balance. I'm not sure that this is something you will ever actually use, but I think it is a decent example of some of the challenges that you have when you start building logs that are intended to be used to solve a specific problem. So, I mean, in summary, what I spent this morning and then this follow-on lecture talking about are the things that we do with distributed logging. Why did we do distributed logging? Well, because logging in general is a really good technique for building transactional systems. We can go from using that in a single transactional system to distributing it so that we have multiple people participating in that, and then we just add that coordinator in there. Or we could actually even go one step further, and that is the log itself becomes something that everybody can see, and we share that with with this distributed log. Whether we did it with the centralized model or we do it with the decentralized global log Corfu model. And then finally, we can actually build specialized logs, things like the secure chain in whatever the name was, the secure blockchain-based logging mechanism, which gives us secure logs that are tamper resistant and provide us with a high degree of security guarantees. So that's actually it. I'm going to rest it here. So the next lecture is going to actually be when we start talking about consensus. So we've got all these tools now. We've built these tools. We've been looking at the problems. We've been working with Project 3 long enough now that you have a pretty good idea of why it's not the best solution, what kinds of limitations it has, and we were fine with that. And now we're going to be talking about, okay, so how do we get beyond that? How do we move to the next level up? Tomorrow we're going to talk about quorum replication. Next week we'll talk about Paxos and Raft. So thanks, and I'll see you on Thursday.